Yes, good morning, everyone. We are going to start with today's lecture. So, let me recall you what we had started yesterday. So, we define an equation. We considered a equation known as heat equation. So, I explained you that it is a partial differential equation, and basically it is modeling the dynamics of heat conduction in different systems. So, this was the heat equation. Del U by del T is a constant times del 2 U by del X2. So, it is having a first order time derivative and a second order space derivative, and in space it is just one dimensional. U is the dependent variable, X and T are independent variables, and physically what U represent is the temperature at any point X at any time T. So we consider the simplest possible example of a metallic rod or a metallic bar. So where which has two ends A and B, there is certain length of the rod which we will be considering, and at any point X of the rod and at any time T, what is going to be the temperature, that is denoted by U, and this K represents a constant in the system. So it has to do with the physical properties of the material of the metal. So we will not be tweaking anything about K, we'll be just treating it as a constant given to us. And then I told you there are second dimensional and three dimensional versions also, but we are going to only look at the one dimensional heat equation. Del U by del T is the constant times del 2U by del X square. Now important point is we want to now solve this partial differential equation. So far the only known techniques to us are the solution of ordinary differential equation, while we do not have any general method known to us so far how to solve this equation. So I'll be introducing the method first with the very simple example, and then we will be applying that method to particularly heat equation, because for PDEs you do not know any method right now. So the method which I'm going to introduce is, firstly I will exemplify that with a simple example which is not the heat equation, but then we will use the same method for the heat equation, right? And then I will be talking more about the initial condition and boundary conditions given to us. So let me first give you the idea of that method. So for I will be explaining with the help of example only. So this method name is separation of variables. Right, so if you are given a partial differential equation, so by finding the solution means you need to find the value of the unknown, the dependent variable. So just like you have, say, this differential equation, this partial differential equation, del u by del x is equal to some constant times, say, del u by del y. I have taken very simple example in which both the derivatives present are the first order derivative, because once you will learn for this first order, then we will be able to apply the method for solving heat equation. And in addition, some condition can be given to you. So here I have considered u is the dependent variable, x and y are the independent variable. So the basis of this method separation of variable is you have to assume that your solution, which is actually going to be a function of x and y, is a particular type. It is x into y, where capital X is a function of x and capital Y is a function of y. So you assume that the solution of this differential equation will be, the final solution will be this form, that product of two different functions, where one function is going to be purely function of x and other function is going to be purely function of y. So what do we mean by that? The examples will be, solutions will be like x square into y cube. You can separately see a pure function of x and a pure function of y, and they are just product with each other, they are multiplied with each other. Other possibilities, e raised to power x sine x into log y, right? So this is going to be capital X, this is going to be capital Y. So we cannot have solution like this, capital X capital Y, because plus minus is not allowed, only multiplication operation is allowed. So that means it's an assumption which assumes that the differential equation, the partial differential equation, is going to have solution like this. Now you can ask a question here, that what if this assumption is false? Because obviously there exist partial differential equations which are not going to have solutions of this type. In that case, what will happen? If you assume this and you keep on doing your calculation, you may arrive at a contradiction. Your calculations will not match, or it will somewhere lead to a contradiction, and then you will say, okay, our assumption was wrong, this method is not applicable. For that differential equation, we will use some other method. But heat equation, wave equation, which we are going to take up in this course, for them it has been well proved that the separation of variables work in finding the solution. That is why I'm going to give you example of this method, right? So this method is based upon this assumption that your solution looks like this. And once you assume your solution to be of this type, then how it is going to help? Now, what is this capital X and what is this capital Y? How we are going to find that? So what you do is, say this is your differential equation. So to substitute in the given differential equation, I need to have two values, del u by del x and del u by del y. So what is going to be del u by del x? It is del by del x of capital X into capital Y, because now I have substituted my assumption that u is looking like capital X into capital Y. So here you can use product rule. So product rule is going to give you y into dx by dx plus, that's it, because y capital only y, it will be differentiated only, x will be differentiated with respect to small x, y will not be differentiated because y is not dependent upon x. Capital X is only function of x and capital Y is a function of y. So when you are partially differentiating x into y with respect to x, so y will be treated as a constant, so that will just come outside, and this will be del x by del x, and the del x by del x actually will be written like dx by dx, because this can be written as a full derivative now, because capital X is just the function of one variable, so its derivative is going to be a full derivative, not the partial derivative. So this is y into x dash. And similarly, del u by del y is going to be del by del y of xy. So this is going to be x y dash, right? So if anybody has any doubt till this point, then you can ask. Okay, this is easy. I'm just computing del u by del x and del u by del y because I need to put them into equation number one. So you put the values of del u by del x, del u by del y in equation number one. You will get yx dash is 4 times x y dash. So now I can rearrange the terms. X dash by x is going to be 4 times y dash by y. So what I'm doing is making all the terms containing x on one side and containing all the terms y on the one side. So left hand side is now purely containing x terms and right hand side containing purely y terms. So this one is purely a function of x and this one is purely a function of y, right? So if you have two functions which are functions of different variables and they are equal all the times, like they are always equal, they are not equal at a particular point, they are always equal. So the only possibility is both of them are going to be equals to some constant, right? So this is a mathematical, you can say reasoning coming in favor of this. If you have a function of different variable and they are always same, so the only way it can happen is each of them is equal to a constant function, right? You cannot have, you know, you cannot have x square is equal to y square uh, for all x y. Means that can represent a solution curve, but it is something like some function is always equal to the value taken by, now whatever are the values taken by x square, whatever are the values taken by y square, how they can be always the same when x and y are different, you know, your x is a different variable, y is a different variable. So this is only going to happen if both of them are equal to a constant, because both of them are different variables. So this is also a step which we will be using in separation of variables, that both of them have to be equal to a constant. So since both of them have to be equal to a constant, so this will further give you two equations. Now x dash by x is also equals to c, and y dash by y, 4 times y dash by y is also equals to c. So now you can solve this one. Now what is this? This is a ordinary differential equation of first order, and this is also a ordinary differential equation of first order, right? So what we have done, we started from a partial differential equation, and then using the method of separation of variables, we are able to reach at two ordinary differential equations. They are completely separated. Now for capital X you can solve separately, for capital Y you can solve separately. This way you will be getting your final answer. So I can quickly do this calculation. X dash by x is equal to c, whatever c can be an arbitrary constant. Yes, can you tell me what is going to be the solution of this? This is a simply first order ordinary differential equation. Yes, what is going to be the solution of this? You can write in chat box or you can raise hand and speak up. Yes, it's easy to see if you're going to solve this one. So this is basically dx by x. What is x dash actually? X dash is dx by dx. With respect to x, it is the derivative taken. So dx by x, dx into 1 by dx is equal to c, which way you will be getting dx by x is equal to c dx, and now you integrate both sides, so log of x is equal to c of x, plus you will be getting some another arbitrary constant. So capital X is going to be e raised to power c1 into e raised to power cx. So this e raised to power c1 is another constant you can put. So this is a solution of this differential equation. And similarly, you can solve this one. So it's 4 times dy by y is equal to c. So it's 4 times dy by y is equal to c dy. This is the again variable separable technique which we are using for the first order differential equation. So this is 4 times log of y is equal to c of y plus c2, and this way, or you can shift the 4 to other side as well, 1 by 4. So this log y is equal to 1 by 4 c2 plus c times y, and capital Y is going to be e raised to power c2 by 4 into e raised to power c y by 4. So capital Y is sum, because this is just an arbitrary constant, b times e raised to power c y by 4. So you got capital X, you got capital Y, so you got your solution. You were looking for u, this is x into y. So x is a e raised to power cx, y is b e raised to power this. So a into b e raised to power c x into e raised to power c y by 4. So a into b, you can call it another constant, say d e raised to power cx e raised to power c y by 4. So this is u x y. So now this is the general solution. Means general solution means as it contains arbitrary constants, right? It contains two constants, d and capital C. So how you are going to determine the value of these constants? You will be given two conditions along with the original equation. This equation, because it contains two derivatives, one with respect to x, one with respect to y, so you will be given two conditions here. I have not given you these conditions, I'm just telling you in general this method of separation of variables, you will be given two conditions. So using those conditions you will be getting the value of d and c. That way you will get a particular solution. So that is the framework of method of separation of variables, but the important point is we need to now apply this technique to solve one dimensional heat equation. So this is our question which we are going to now follow up. Yes, Agrim?
मैम प्लीज ऊपर कर सकते हैं, अभी लिखा नहीं है मैम, नोट नहीं
Okay.
किया।
I'll share the notes, otherwise आप note down तो बाद में भी कर सकते हो.
मैम 2 मिनट कर दो मैम प्लीज।
Here is
थैंक यू।
fine.
यस मैम।
Yes, Uday.
मैम ये जो हमने कांस्टेंट लिखा था मैम, मैम ऐसा भी तो हो सकता है कि वो जो x बाय x डैश बाय x और 4y डैश बाय y दोनों फंक्शन की इक्वेशन सेम आ रही हो, जिससे तो पूरे डोमेन में उनकी वैल्यू सेम आ रही हो, कांस्टेंट ना रहे, चेंज होती रहे, लेकिन दोनों की वैल्यू सेम आ रही हो, ऐसा भी तो हो सकता है।
No, it's not happening. Na, see, we are saying they're always equal. How there are two variables, right? One is let's understand it physically. Like one is say time, one is space variable, because this is what is going to happen in the partial differential equations. One of them is usually the time variable, one of them is the space variable. So how come there is a function which is a function of time and there is a function of space? They're always equal. So means because see, when do you say two functions are equal? Let me just ask you this question. If you even have the function of same variable, when do we say they are equal? They are saying to be equal if they are equal at every value of x, right? Whatever be their domain, every value of x. But the point is here we are not having this situation. Here we are having situations, they are having different domains, their domains. So this and this are independent of each other, right? So if whatever x you substitute and whatever y you substitute, the values are always going to remain same. So that means this is clearly not depending upon x, because whatever y you, and this is not depending upon y, because I hope that my point is clear, because whatever you substitute there, they have to remain same. So that is only possible when this will be independent of x and this will be independent of y. That means they have to be a constant function. Because if they start depending upon x and start depending upon y, so you can't equate two functions having different domains. So this is coming from there. You try to think about it with the help of a real example, just like
Okay,
space and time. So this is not going to happen. So this is only going to happen if both of them are equal to a constant.
but there are equations now, for example x square equal to y square, you were also talking about it. What if it becomes like that?
This is actually representing a curve. This is actually going to represent a curve.
Yes, ma'am, and the
This
points
is
on
the
this curve is
solution curve.
satisfied.
Yeah, but points on this curve is satisfied. That's a different, this is kind of, we are solving an equation, we are drawing a curve. But here we are not saying the solution. This is not the solution. This is just a, this is not representing solution. This is yet to be solved, right? This is not whatever it is going to represent. It has mathematically no meaning to our system, right? So whatever this form will come, like you saw this particular example, uh, what does this represent and what does this represent? They are going to be function of x and function of y. So even if you get something like this, so there is no point. Means what is capital X individually and what is capital Y individually? How will you know that? And how from here you will be finding u, which is going to be a function of x and function of y. So that is mathematically not leading to any particular thing, right? Which is not useful to us.
Okay.
I'll give you more intuitive understanding for the same, but let me just go ahead with the next thing, where we will be applying the same technique to solve the heat equation. Right, so shall I go ahead? Right, so this is the question. Basically, determine the solution of one dimensional heat equation. So heat equation is also known as diffusion equation. There is a reason behind it, because physically it represents diffusion. Diffusion is a physical phenomena, but let's not go into detail for that. It's also known as diffusion equation in case you encounter this term anywhere. So you should not get confused, right? So solve, determine the solution of one dimensional heat equation when both ends of the metallic bar are kept at zero temperature, and initially temperature of the bar is given, right? So firstly, let's understand this statement. So we need to solve the heat equation, means del u by del t is equal to k times del 2u by del x2. Equivalently, we can write it like del 2u by del x2 is 1 by k times del u by del t. It does not matter whichever side you keep the constant k. Mathematically, it's more convenient to handle on this side, on that first order derivative side. So that's why just shifting to its side. Otherwise, no reason for it. So this is our equation. And yesterday I told you that how many conditions you will be given with it. You will be given 3 conditions, just like the previous question. There were 2 conditions. There should be 2 conditions given to you. So here there will be 3 conditions given to you. One condition will be for time, and that condition will be known as the initial condition, and there will be 2 boundary conditions given to you. So because first order time derivative is there, so because of for the time you will be given 1 condition. So time means, let me give you the example of the ordinary differential equation. Say in ODE we have dx by dt is equal to some function of x and t. Suppose you have a general first order ordinary differential equation. Then to find its solution, means if you want to call it a initial value problem, so you will be given 1 condition because it is first order. And how does that condition looks? That what is the value of x at time t is equal to 0. So that is given to you. So that can be a constant also, whatever it can be. Say some value is given to you. X at 0 is 0 or x at 0 is 3. These kind of questions you have done in the chapter of Laplace transform as well as in the first chapter, which we call IVPs. You are given initial conditions at time t is equal to 0. If it is for second order, so we have say d2y by dt2 plus dy by dt plus y is equal to, say whatever, I'm just giving you random example. So usually we are given this, whatever, we are given some values. So these problems fall into the category of initial value problem because the conditions specified are at the same point, 0 and 0. And what are these conditions representing? These conditions are representing the with respect to time. So this underlying variable is time. That is why you are given the value of the function and its derivative at initial time t is equal to 0. So same is here, because of this presence of del u by del t, since it is first order, so there will be 1 initial condition. Like these were 2 initial conditions because in time there was a second order derivative present. So 2 initial conditions you required, right? One for y and one for y dash. But here, since with respect to time there is just one first order derivative, so there will be 1 initial condition, and similar logic will apply with respect to space. So with respect to space you will be given 2 conditions, and usually what happens, because you need 2 conditions with respect to space, usually they are the boundary conditions, because boundary conditions are going to help you to determine your final solution. Now what do you mean by boundary conditions? Boundary condition means, say you have a metallic bar, for example this, it has 2 ends, a and b. So you will be given the information of your temperature function at the boundaries. U is your unknown, you want to know u, you do not know u at these points, right? At all the points of the rod you want to know u, how u is a function of x and t for all x and for all t. But at boundaries, this information about temperature is given to you at boundaries. This should be given to us because mathematically we need it. You will see that when we will be solving, we need these mathematically because it's a requirement of the differential equation. Without these conditions, we will not be able to solve it. We'll be just having too many arbitrary constants. We need to get rid of those arbitrary constants. For that we need conditions. So one of the way is you are given temperature at the boundaries. So now if you read the statement which I just have written here, both ends of the bar are kept at zero temperature, right? So something they have given to you, something. So this is one form of boundary condition, that they have told you that this is going to be the temperature at the boundaries. So now the both ends are kept at zero temperature means this is happening for all times. It's not like initially they were at zero and then they changed. We need the information at the boundary at all the times. That means u, which is a function of t, right? X and t. Now at a, the left hand point, mathematically it is x is equal to 0, and the right hand point, mathematically this is x is equal to L, L being the length of the rod, because x, you have to start your measurement of x from somewhere. So it's usually the left hand point which is a reference point, we call it x equals to 0, and the right hand point is that x is equal to L, capital L be the length of the rod. So this is 0 and L. U is given to you for all the times. So T has been written like this at 2 points. What 2 points? X is equal to 0 and at x is equal to L. Now what is this given to you? So this can be any value. Like in this particular question which we are going to solve, it is given as 0. So this is the actually simplest possible boundary conditions. Later on, when you will be efficient in solving this differential equation, later on you can try with the different boundary conditions, but you will see the things will get mathematically complicated. That is why we want to first consider the simplest case, and this is the simplest case when the both ends are maintained at zero temperature for all the times. So this is about the boundary conditions. These two are known as the boundary conditions. And what else? Initially temperature is given. So some initial temperature profile is given to you. This also explained to you yesterday. Initial condition will look like mathematically. Now T is equal to 0. Initially means T is equal to 0, but X is anything. X can be having any value. So initially you know the temperature function for all values of X. You know the temperature here also, here also, here also. So at all the points of the metallic bar, you initially means your beginning point, you know the temperature. Now this can be a constant or this can be a function also. Now if it is going to be a function, this is going to be a function of x, because t has been already substituted, 0. So this initial temperature profile is going to be a function of x, or it can be a constant value also. So this is known as, this condition is known as initial condition. Now particularly in this question, so far we are not given any initial condition. We'll come to this. We will, because this has to be utilized in the end, because you remember when we were solving initial value problems, we completely used to solve the differential equation, and the given initial conditions are only to be used in the end when we obtain the general solution. So same will be done here. The initial condition is going to be used in the very last. So there we can have its information that what it is. It can be a constant, it can be a function. So it can be sine x also, it can be x also, it can be 0 also, a constant also, whatever it is, it's just given to you. So this does not affect the things much, but these boundary conditions play important role. They are going to handle the mathematical complications. So that's why they have been taken to be simplest possible, which is 0. Right? So now let me go ahead with the solution, that this is the equation and these are the boundary conditions, and this is some initial condition is there. Particular initial condition, we will take up that in the last. So now we are going to use which method? Separation of variables. Now let me again write your equation. So your differential equation, your heat equation is uxx is 1 by k times ut, right? It's ut is equal to k uxx, but I told you will be better keeping this k on the time derivative side. It's easier to handle mathematically. So You can do it this way. So what is that first step? So you have to assume your solution is like capital X into capital T, where capital X is purely a function of X and capital T is a function of T only. So small x is denoting the space, small t is denoting the time. So we assume according to the method of separation variables that this is going to happen. Now this is your condition, this is your differential equation. So you need to find ut, means del u by del t, and you need to find uxx. So differentiate, so I'm calling this equation 2. Equation 2 partially with respect to t. So when you differentiate partially with respect to t, on left hand side I will be getting del u by del t, and on right hand side I will be getting del by del t of x into t. So x will be turning outside. Actually this will convert to d by dt because t is a function of just one variable, as I explained to you. So this is going to be xt dash. And similarly del u by del x, when you differentiate equation 2 partially with respect to x, so del u by del x is going to be del by del x of xt. So this is x dash into t. And what is del to u by del x2? So this is one more time you differentiate with respect to x, because with respect to x I need second order derivative. So that's why one time and then second time with respect to x. So it is going to be x double dash into t. T is just going to behave as a constant for when you are differentiating with respect to x. So now you put the values coming from 3 and 4 in given equation 1. So you put the 3 and 4 in equation 1. So on left hand side you have del 2u by del x2 is equal to 1 by k times del u by del t. So that is xt dash. X double dash t is going to be same as this. So from here you will get x double dash by x is equal to t dash by kt, and they have to be equal to a constant. Let that constant be omega, right? So this is the same logic. One function is a function of x, another function is a function of t only. So this is going to happen only each of them is equal to a constant. So let that constant value be equals to omega. So why I have taken this omega? I could take this c also, but it's going to have some physical significance. I'll tell you that later why I have taken this omega. Otherwise notation doesn't matter, whatever you can take. Right. So from here you will get two ordinary differential equations. One is x double dash by x is omega, and other is t dash by kt is omega. Right. So this one is a second order ordinary differential equation. This one is a first order ordinary differential equation. So let me call this equation number 5. Let me call this equation number 6. Right. So this is d2x by dx2 1 by x is equal to omega. So this is basically right. I'm now writing it in this form d2x by, I'm firstly focusing on equation number 5. d2x by dx square minus omega x is equal to 0. Yes, can you solve this one? So here actually what will happen, we'll have three different cases. We will have cases depending upon omega. So omega was the constant which we introduced. Now this constant can be positive, this constant can be negative, this constant can be 0. So from here onwards there will be three further cases. But before going towards those cases, so let us again look at the boundary conditions. So what were the given boundary conditions? Original given boundary conditions were, because we have to now use boundary conditions. Boundary conditions which were original given to you is Is it fine? Now, since we are no more working for u will be introduced in the last. Our u is a function of x and t. Firstly, we are working on finding capital X and capital T, right? So our boundary conditions which are given to us are in terms of u. So I need to first to convert the boundary conditions also in terms of x and t. And since t has nothing to do with the boundary conditions, t is a function of time, so the boundary conditions are going to be translated purely in terms of x. You will see that yourself. So these boundary conditions which are given to me, I will be using them and transforming them to the variables capital X and capital T. So u at 0 comma t is 0, that is given to me, and just a minute, yeah. So let me just use that. U at 0 comma t is 0 and u at L comma t is 0. These are the boundary conditions given to me. Now what is u, which you have assumed? U is x into t. So basically, let me write it in this form. So if you put x is equal to 0 and t is equal to t, small t is small t, but small x is 0, because I want to use this one. So u at 0 comma t is given to you 0 is equal to x into 0 t into t. Yes, this implies x into 0 is 0 because t is non-zero. What is t? T is actually denoting the function of t. Capital T is a function of t. So why this has to be non-zero? Because if this capital T is 0 at all the times, then according to this solution, your uxt is going to be 0 always, right? So at all points of space, at all points of time, at all x and all t, your function is going to, your temperature is going to take value 0. So this solution is known as the trivial solution. So trivial solutions are something like which are appearing mathematically, but physically they have to be ignored. It is meaningless, right? That for all times and at for all points of the rod, the temperature is 0, because initially some temperature was there and then the rod started cooling down. So there will be different temperature profiles occurring. So it is physically not possible that you have a 0 solution, or mathematically you can say this is the trivial solution. Trivial solution means nothing is left. If nothing is changing, then there is no point of writing the differential equation for it, right? Everything is just constant equals to 0. So that means there is no point of talking about del u by del t and del 2u by del x square. All these are also going to be 0. So that means we are just ignoring the trivial solution. So from due to this reason, this capital T has to be non-zero. So therefore, from this I get x0 is equal to 0. So that means the first boundary condition translated to this in terms of x. Similarly, let's look at the second boundary condition. The second boundary condition, again for that, let me write u. So now you put x is equal to L. So when you put x is equal to L and t is equal to t, so this is also given to me 0. So due to the same reasoning, the same logic which I gave you, this way you will get x at L is 0. So these are the, you can say now, boundary conditions. They were also boundary conditions which were given to you. They were given to you for the function u. But since now we are not talking about u, we are talking about capital X and capital T separately. So this capital X, capital T, this capital X, this equation, let me call this equation. So this is now having two boundary conditions, and those boundary conditions which we have derived are x0 is 0, x at L is 0. So now this becomes a complete system. You can find its solution, right? Please ask up till this point if you have some doubt. Is it fine? Right? So we derived this second order differential equation, and then now it is purely a function of x. For the time being, you just forget t. So this is having two conditions with itself, x at 0 and x at L. And how those two conditions are derived, x at 0 is 0 and x at L is 0, from the original boundary conditions which were given to me for the function u. So using the definition of u and using this logic that I need to ignore the trivial solution, so we used this. Yes. So if you want me to explain this trivial solution part again, trivial solution means some things which are just mathematically coming, but physically they are meaningless. Right? So this trivial solution means that temperature is always 0. So that means whatever you do with the rod initially, even if you give some temperature profile. So initially some temperature should be given to you. We are not given the initial condition, but suppose initially some temperature is given to you, that these are the this is how the initially, like yesterday explained you, initially you heat up the rod and you attain a temperature at left hand side, and then you attain a temperature at right hand side, and then slowly the rod starts cooling down itself. So that means when the rod is cooling itself, so it's not possible that it is maintaining a constant temperature all the time. So this is a zero solution, it's a trivial solution. So we need to find a non-zero solution. So that's why we ignored this case. Ignored means it's not possible that this capital T is always zero. So therefore, because the product of two number is zero, I have written capital X at 0 into T is 0. If this is non-zero, so this has to be 0. Similarly, X at L also has to be 0, because we are looking for the non-trivial solutions of the differential equation. Right? Do not get confused with the word trivial, non-trivial if you don't want to remember that as a word, but it is just, you can say that uh, it's something like, if I'm going to solve the equation x is equal to y, then the trivial solution is x is equal to y is equal to 0. Like this is always satisfying. But non-zero, non-trivial solutions are, it can have 1 is equal to 1, 2 is equal to 2, or 3 is equal to 3, something like that. So these are the solutions which are coming from this kind of system. Yes, see, I explained that again. Okay, Arpit. So this part which I explained, that why they are equal to a constant. If both of them are functions, then why they are individually equals to a constant. So this is, see, there are two functions. One is a function of a different variable and one is a function of different variable. How they are always equal? They are always equal means, uh, let me explain to you again. Say you have this, one is a function of variable x and one is a function of variable y. So whatever x you choose and whatever y you choose, they are going to be same. Whatever x, f1 is same as g2, f3 is same as g2, f4 is same as g2, f9 is same as g100, whatever, right? They are always equal, no condition at x and y. So if they're always going to be equal, so that means it does not matter what x you choose, what y you choose. So that means this f and g are actually becoming independent of their variables. F is not depending on x and g is not depending on y. So that is only possible if they are constants. The constant function is the function which does not depend upon the domain. It takes the same value all the time, right? Is it clear? Right? So this is the logic we are using here, because they are function of different variables. Had they been function of the same variable, we could have got some result out of it, but because they are function of different variables, that's why it's not happening. So this point I am explaining again because we are using it frequently in this method of separation of variables. So this was the explanation for this point. Now from this point onwards, we have now two separate ordinary differential equations. So firstly, I'm going to put my all focus on equation number 5. which is actually a second order differential equation. Now to find its solution of this second order differential equation, if I want to find its particular solution, obviously I'll be following the same process. Firstly, I'll be finding the general solution, and then I'll be finding the values of the two arbitrary constants introduced by using the boundary conditions. So, but now from where those conditions are coming? So you can see the conditions are given to you in the question, but these are given to you for the function u. I want to transform them into the language where I can use them for this differential equation, which is actually for x. So that is why we did this calculation and figured out that these are the new, means they are nothing new, but these are the same conditions just transformed in the language of x. So now you have equation number 5 supplemented with the new boundary conditions. I think I'll stop here because now we need to solve it further, and now this will depend upon the value of omega, because depending upon the value of omega, it will have different types of solutions. So we will discuss from this point onwards in the next lecture. Right? So now you can ask me if you have doubts.
मैम इस इक्वेशन के मैम सीधा दो बार इंटीग्रेट नहीं कर सकते मैम x के रिस्पेक्ट में?
नहीं, सॉल्व जैसे मर्जी करो, वो तो आपका तरीका है, सॉल्व कैसे भी करो, सॉल्यूशन आ जाएगा। मैं आप बाउंड्री कंडीशंस की बात कर रही हूँ, वो उस बात पे तो भी आएंगे ना कि सॉल्यूशन कैसे करना है। वो तो एक सेकंड ऑर्डर ओडीई है, वो तो आपको जितने भी तरीके सिखाए आप दो बार इंटीग्रेट कर लो या ऑक्सिलरी इक्वेशन वाला मेथड यूज कर लो। इसको हम ऑक्सिलरी इक्वेशन लिखेंगे तो m स्क्वायर माइनस ओमेगा बनेगा, फिर ओमेगा के ऊपर डिपेंड करेगा कि ओमेगा रियल है, इसके रियल रूट्स आए कि कॉम्प्लेक्स रूट्स आए। रिमेंबर सेकंड ऑर्डर के लिए हम ऐसे ही करते थे कि जनरल सॉल्यूशन में एक्सपोनेंशियल होगा कि साइन कॉस होगा, क्या होगा। सो वो आपके ऑक्सिलरी इक्वेशन के रूट्स पे डिपेंड करेगा, क्योंकि यहाँ से आ जाएगा प्लस माइनस स्क्वायर रूट ओमेगा। अब ओमेगा अगर 0 है तो ये दो रूट आ जाएंगे इक्वल। ओमेगा रियल है तो रियल एंड डिस्टिंक्ट रूट्स आएंगे। ओमेगा नेगेटिव है तो इमेजिनरी रूट्स आएंगे। तो दैट्स वाई यहाँ से अब 3 केसेस बनेंगे हमारे ओमेगा के, एंड देन वी विल फाइंड अ सॉल्यूशन ऑफ इट। आप कैसे भी सॉल्व करो, बट ऑब्वियसली ओमेगा पे डिपेंडेंसी रहेगी आपके सॉल्यूशन की। राइट, सो विल कंटिन्यू फ्रॉम दिस पॉइंट ऑनवर्ड। यस अग्रिम, यू हैव अ डाउट?
नो मैम, वो पहले से उठा रहे, आई लोअर इट।
ठीक है। Okay, then in the next class we'll finish this solution of heat equation. It's a lengthy one because there are so many mathematical things also need to be explained simultaneously. So it will take time, at least till the next complete lecture, when we'll be able to solve this equation. Right, so that's all for today. Yeah, thank you.